Sometimes we're going to find ourselves with a difficult differential equation, and it's going to be possible to take the Laplace transform of both sides to make it an easy differential equation. Then we'll solve the easy one and take an inverse Laplace transform to convert the answer back to a solution of our original equation. So this raises two questions. When can we take a Laplace transform? And then after we do, how do we take an inverse Laplace transform? So again, the plan is, if the differential equation is difficult, we'll take the Laplace transform of both sides. Then we'll solve the hopefully easier differential equation that we get. And then we'll use an inverse Laplace transform on the solution to convert it into a solution of the original differential equation. So then, as I said, this raises two questions. First of all, for which functions f can we take L bracket f, the Laplace transform? And then how do we invert this process? At the end, because we have to convert the Laplace transformed solution into a solution of the original equation. All right, so let's look at, first of all, which functions we can take a Laplace transform of. So it turns out it's going to be almost all the functions that we want to. So the Laplace transform of f of t is defined as long as the integral that we use to define it converges. Oops, I forgot a minus sign here. E to the negative st f of t dt. So it turns out that this converges for f of t equal to a polynomial in t an exponential function, so e to the at, something like that, sine of bt, cosine bt, and any sum of these. So we just need f of t to satisfy absolute value of f of t is less than or equal to me to the alpha t for some numbers m and alpha in the real numbers. So we just need to have a function that grows no faster than some exponential function. So it's actually harder to come up with an example that grows faster than exponential that we would not be able to take the Laplace transform of. So it does not converge for, so something that grows faster than e to the t would be e to the t or e to the t squared or something like that. So we need to use compound exponential functions to get something that grows too fast for the integral to converge. Alright, so now let's talk about the inverse. So the best way to invert, I think, is to use a table. Now, first of all, since L is linear, that is L of f plus cg equals L of f plus c L of g for f and g functions and c a real number. So since it's linear and its inverse is linear also, so it'll satisfy the same property. So let's draw a table of what we know about inverse, so about what we know about Laplace transforms. Because the inverse of a function is just whatever it takes to get that function. So if we want to take Laplace inverse of f of s, this is whatever function f of t satisfies Laplace transform of f of t equals capital F of s. So it might not sound like a very explicit definition because it doesn't tell us what to do, but that's what inverse means. It means whatever it takes to get this. So if f of t is what it takes to get this, then f of t is the inverse of this. So let's make a table of what we know about Laplace transforms, and then sort of reading the table backwards is going to be our inverse Laplace transform. So we'll make one column for functions f of t and another column for Laplace transform. We'll call this one capital F of s. So we said that if we have t to the n, then the Laplace transform is going to be n factorial over s to the n plus 1. We said that if we have e to the at, here I'm thinking of n as a non-negative integer. we have e to the at where a is a real number. We said that this gives us 1 over s minus a. And the restrictions on s here are, for the first one, s is greater than 0. For the second one, s is greater than a. For sine of bt, where b is a real number, the Laplace transform is b over s squared plus b squared. And that works for s greater than 0. Cosine of bt is similar. That's s over s squared plus b squared. And then, running out of space here, one new entry that the book put in this section, even though we didn't discuss it in the other section, is 1 over square root of t. And the Laplace, I'm running out of space, the Laplace transform of that is square root of pi over s. For s greater than 0. All right, so if we get a function that's a linear combination of these, we can take the inverse transform of each of them one at a time, convert them to this side, and then that'll be the inverse Laplace transform of the sum. So let's do some examples. So let's take the inverse Laplace transform of 4 over s. Now if we look at the right hand side, this looks a little bit like the first entry here. We've got number over a power of s. So to undo that, I guess we have to express the power of s as something plus 1. And since this is linear, the number can come out. I don't know if the number is going to, well, 4 is not going to be factorial of anything, because 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6. So 4 is not going to end up being the right factorial, so let's just take it out. 4 times inverse Laplace transform of 1 over s. I'll write this as 0 plus 1. Alright, then I wish I had 0 factorial in the numerator. Actually I do, because 0 factorial is 1. Alright, so the inverse Laplace transform of 0 factorial over s to the 0 plus 1 is t to the 0. So copy the constant, t to the 0. T to the 0th is just 1, so this is 4. Alright, let's do another example. So we're just trying to make our function look like something on the right hand side of this table, and then we'll just go to the left hand side for the corresponding function there. So let's raise the power. Negative 3 over s squared. What's the inverse Laplace transform of this? Well, we've got a power here, so we'll try and use this first entry again. Negative 3 is definitely not factorial of anything, so negative 3 L inverse of 1 over s to the 1 plus 1, because it helps if we write this as s to the something plus 1. And then I wish I had a 1 factorial in the numerator, and actually I do, because 1 factorial is 1. And then I go backwards and see that t to the 1 is the function whose Laplace transform is this. So it's negative 3 t to the first power, or negative 3t. All right, let's do another example. Let's take the Laplace inverse of the inverse Laplace transform of 12 over s cubed. And I'll write this as 2 plus 1, and then wish I had 2 factorial in the numerator. 2 factorial is 2. So I guess instead of pulling the 12 out, I could pull 6 out and leave 2 there, because I'm going to wish I had 2 there anyway. So I'm going to write 6 L inverse 2 over s to the 2 plus 1. 2 factorial is the same as 2. Now if I have 2 factorial over s to the 2 plus 1, the inverse Laplace transform of that is t squared. So this is going to be 6 t squared. Okay, maybe I've done enough with this first row. Let's pick a function that's in one of the other rows. Let's take the inverse Laplace transform of 4 over s squared plus 9. All right, s squared plus 9 is s squared plus something squared. That's 3 squared. And then we have a number in the numerator, not the variable s, but a number. So I kind of wish that that number were 3, because then we'd have 3 over s squared plus 3 squared. So let me pull the 4 out. 4 L inverse 1 over s squared plus 3 squared. And then I want to put a 3 in there. So why don't I multiply by 3 over 3? I'll keep the over 3 on the outside, and I'll put the 3 on the inside. And now it matches our pattern here. This is 3 over s squared plus 3 squared. So that's going to turn into sine of 3t. So that's 4/3 sine of 3t. Alright, let's make it a little bit more complicated. We haven't had to use linear combinations yet. What if we have L inverse of 2s plus 5 s squared plus 3 squared? So I'll keep the denominator from the previous example. So now we have an s and a number in the numerator. Well, we can write this fraction as 2s over the denominator plus 5 over the denominator, and then tackle each one separately. So this is L inverse of 2s over s squared plus 3 squared plus L inverse of 5 over s squared plus 3 squared. Alright, now we have an entry for s over s squared plus 3 squared, but without the 2. So let's take the 2 out. And then that's 2 L inverse s over s squared plus 3 squared. And then how about here? So here I wish I had a 3 for my number in the numerator, because then it would be 3 over s squared plus 3 squared. So let me take the 5 out. Let me put a 3 there and divide by 3 on the outside so I'm not lying. And then I think this is in a form where we can just go back. So L inverse of s over s squared plus 3 squared is going to be cosine of 3t. So 2 cosine of 3t plus 5/3 L inverse of 3 over s squared plus 3 squared, you said, is sine 3t. Sine of 3t. So that's the inverse Laplace transform of this function, 4 over s squared plus 9. All right, now we didn't do any exponentials yet. Let's do an exponential example. Let's take the inverse Laplace transform of e to the 2t plus 6 e to the 3t. Oh, actually I'm doing this wrong. I picked a function that's on this side. I wanted to pick 1 over s minus something. All right, let's take L inverse of 2 over s minus 3 plus 4. Ooh, I'm going off the board, going off the screen. Two over s minus 3 plus 4 over s minus 6. So we can separate this out. All of our fractions over s minus something have a 1 on the top. So let's take out the numerators. This is 2 L inverse of 1 over s minus 3 plus 4 L inverse of 1 over s minus 6. Now for 1 over s minus 3, we get e to the 3t. So 2 times e to the 3t plus 4 times 1 over s minus 6 turns into e to the 6t. So 4e to the 6t. All right, easy enough. Now sometimes we're going to see a function that doesn't look like anything in the table, but we can play with it actually to turn it into something in the table. So here's a harder example. What's L inverse of s plus 1 over s squared minus 7s plus 6? All right. It looks a little bit like s squared plus something, except for the minus 7s, which doesn't fit that pattern. Now you might remember from calculus that we can write fractions like this as 1 over s minus something plus 1 over s minus something, possibly with different numerators. So we can use partial fractions to express this as a sum of things that look like 1 over s minus a number. So we write s plus 1 over, let's see, we need to factor the bottom for this to work. That's s minus 6 times s minus 1, I think. S minus 6s minus s, so minus 7s plus 6. Okay, so that is the denominator. And that should be expressible as something over s minus 1 plus something over s minus 6. Now we just need to solve for a and b. Now these should hold for all s, which means that a good strategy is to plug in an s. Well, if we multiply through, plug in an s, it's going to make something disappear. So if we multiply both sides by s minus 1 times s minus 6, that leaves us with s plus 1 on the left-hand side equals, if we multiply by s minus 1 times s minus 6 here, the s minus 1 and s minus 1 are going to cancel. So we'll have a times s minus 6 plus b s minus 1 for the same reason, because the s minus 6 and the s minus 6 will cancel. Then the first two good choices of numbers to plug in for s are s equals 6 and s equals 1. So when s equals 6, we have 7 equals a times 0, that disappears, b times 5. So that means that b equals 7/5. And then what happens when s equals 1? When s equals 1, we have 2 equals a times 1 minus 6. A times negative 5 plus b times 0. So the b drops out. So that means that a equals negative 2/5 if we divide both sides by negative 5. So that means that L inverse of s plus 1 over s squared minus 7s plus 6 equals, so a is negative 2/5. Negative 2/5 L inverse of 1 over s minus 1. B is 7/5 plus 7/5 L inverse of 1 over s minus 6. And that equals, let's see, 1 over s minus 1 is going to translate into e to the t, e to the 1t. So negative 2/5 e to the t plus 7/5 1 over s minus 6 is going to translate into e to the 6t. So there we have it. So there's two things we need to do for Laplace, inverse Laplace transforms. We need to remember this table so that we can find functions over here and then move to the left to the corresponding function on the left-hand side. And we need to take linear combinations, and the trickiest thing that could happen, I guess, is we get a fraction that doesn't look like any of these, and then we have to use partial fractions so that we can express the complicated fraction in terms of easier things that we can look up in our table. The end.